Welcome to linear non-homogeneous first order equations in theory. So recall linear non-homogeneous first order essentially means that our equation is y prime plus p of xy is equal to q of x. And also recall that y prime plus p of xy equaling 0 homogeneous equation has solution y is equal to c e to the negative integral of p of x dx. So what we are going to do to solve the non-homogeneous equations is we are going to take advantage of the fact that we do know how to solve the corresponding homogeneous equation. So we are going to take advantage of the fact that we know how to solve the corresponding homogeneous equation. Which is y prime plus p of xy equals 0. And we are going to essentially assume that our solution to the non-homogeneous equation can be expressed as some function times the homogeneous solution. So we're going to replace a c in the homogeneous solution with an unknown function u of x, and then hope that we can find some u of x that will then satisfy our non-homogeneous solution. So this equation, so this is what is called variation of parameters. So to solve y prime plus p of xy equals q of x, the first thing that we are going to do is first solve the homogeneous equation. So solve the corresponding homogeneous equation. Of y prime plus p of xy equals 0, and we just need one function, and so we just need one solution. And so we can just pick y1 equals e to the negative integral of p of x dx. Then what we're going to do is we are going to assume y equals u of x times y1 is a solution to the non-homogeneous equation. So we're assuming this is a solution to y prime plus p of xy equals q of x. So this replacing of c with the replacing of the constant c with a function u of x is what makes this called variation of parameters. And this is a technique we will see multiple times throughout this course. So from here, we're just going to solve for u. So we know that y prime is u prime times y1 plus u times y1 prime. And we know that this is y is a solution to our non-homogeneous equation. So we have u prime y1 plus u y1 prime plus p of x times u times y1 is equal to q of x. And then if we rearrange this, we have u prime y1 plus, I'm going to pull out a u from the next two terms. We have y1 prime plus p of x y1. And that whole thing is being multiplied by u. We're saying this is equal to q of x. From here, y1 prime plus p of x times y1, that should be equal to 0. Because y1 is a homogeneous solution. And so what we are now looking at then is we have u prime times y1 is equal to q of x. Or u prime is equal to q of x over y1. And if we integrate both sides, you have the integral of u prime dx is equal to the integral of q of x over y1 dx. And therefore, u is equal to the integral of q of x over y1 dx. I'm going to write the plus c sort of on the outside. Oh, my screen's not updating. One moment. So I'm going to just write my plus c straight out here. Then we have our original solution, which was y equals u times y1. We have then that y is equal to, I'm going to do y1 out front, y1 times the integral of q of x over y1 dx plus c, or in other words, y equals y1 times the integral of q of x over y1 dx plus c times y1. So notice this first piece, y1 times the integral of q of x over y1 dx, is just a one non-homogeneous solution. That c times y1 is actually the general homogeneous solution. And from here, we have our general sort of formula for our solution. So as long as we can find that y1, we can solve for u, and then solve for our overall non-homogeneous general solution. Just a quick note, sometimes the integrals are not actually possible to do by hand, and so you may have to leave your final result with an integral in the formula, in the format. So sometimes you'll run into an integral that cannot be solved. Or at least that cannot be solved by hand. And if that's the case, then just leave the integral in your solution. So in the next video, we will do some examples with variation of parameters. And I'll do one where I kind of rework through just the background, as well as some where I just skip ahead using the formulas.